Okay, guys, so here is that problem that we were looking at the end of class. You've got some particle that experiences some weird force, and it has some mass and some starting position and some velocity. Okay, the most important thing you can do whenever you see any problem, your first step, no matter how good or how bad you are at physics, your very first step should be to make your own picture of the problem. You got to get rid of all these words, okay? So my picture of this problem looks something like this. This is a problem that takes place in one dimension along the x-axis. Here is where I start, 30 meters. Here's where I end. My velocity is negative, so notice I have the velocity pointing toward the origin and the force points away from the origin, okay? We said at the end of the class that we were going to use the same technique for this problem that we used for this more familiar problem of throwing a ball up into the air with some minimum speed v0 and finding the maximum height that that ball goes to. So, namely, we're going to use work energy theorem. Okay, so work energy theorem looks a little bit different for this problem, though, only insofar as our formula for work looks a little bit different. So the idea is this force changes depending upon where you are. So I can't just say force times distance. That's not going to work because every time I'm at a different distance, I need to plug in a different value for x, okay? And so the general strategy is if you have something that's changing, if your force is changing, you can still find the work, but you can only find a little tiny piece of the work over a very small region. In other words, you look at how much work it takes to move the particle here, and then how much work it takes to move the particle here, and here, and the only way that you're actually allowed to plug in a value is if you make these intervals so small that they're infinitesimal. And then for each dw, then you can pick a particular value for x and you can plug it in. But of course, you know from your calc class that if you have to add up an infinite number of infinitesimal things, really what you're doing is an integral. Okay, so that's how we get to that integral. But other than that, other than the integral, this problem looks a lot like the simpler ones that we did in class. So here, let me set up the integral. So I'm going to start at x equals 30. I'm going to end at x minimum, wherever that is, okay? And then this is f dot dx. So one thing that might be a little confusing here is, wait a minute, I thought the particle was moving this way and the force is that way. Shouldn't there be even another minus sign here or something like that? Well, actually, no, because what we're doing, the way we've set the integral up, we're actually taking dx to be in this direction. Dx is in this direction. So we're kind of, the way the integral's set up, we're kind of integrating backwards. We're starting here and we're going this way. So dx and f both point in the positive x direction. All the minus signs and stuff will get taken care of because ultimately x minimum is a smaller number than x maximum. And so a way you can think about it is kind of that is what reflects the fact that we're moving backwards. But we're going to let dx run in the positive direction. And so this dot product we don't get. So you have a dot b is a b cosine theta. Our theta is actually 0 degrees. So that's why there's no minus sign. Okay, so that's that. If you do this integral, you'll end up with this. If you evaluate at the limits, you'll end up with this. Okay, and then that's the work. That's the work. And so what do you do with that? You set it equal to the kinetic energy, a half mv final squared minus a half mv initial squared. Okay, and so if you work out the algebra, you'll end up with some number about that. So it's a small number. It's 0.024 meters. So this is obviously not to scale. This is small. Okay, and that's it. That's the problem. So I made this force up. This is pretend, but we are going to spend our time studying something called Coulomb's law later. And Coulomb's law looks like this. Okay, and that means that it is a function of r, and we are going to spend an entire chapter talking about something called voltage, which is the work done by electric forces. Okay, so this sort of calculation, if it's a little unfamiliar now, hopefully by the time we start doing this stuff, you'll be an expert at these sorts of calculations by the end. Okay, if you guys have any questions about this, please ask.